I'm Yoshi. I actually moved to Dartmouth College. I applied for this school from when I was still in Hokkaido, so I still have my affiliation in Hokkaido, but that's probably why I decided to talk a little bit about West Antarctic and East Antarctic, where I actually did the work about East Antarctic when I was in Japan. So anyway, I'll go quickly, but Antarctica is losing ice, right? As you know, we see some hotspots. It's not losing ice everywhere equally, but there are some hotspots. Amundsen Sea is one of them. This is Totten. This is the two different regions that we are focusing on in this talk today. So I believe some of you already know about this, but when you look at this is the highest melting region. This is Amundsen Sea. What we see is this warm circumpolar deep water. This CDW. This is the term, I think, one abbreviation that I might be repeating using in this talk. So CDW is important one. This warm circumpolar deep water. This water mass is flowing all the way towards the ice shelf cavity. This is the observations. You see this warm water flowing all the way to the ice shelf cavities. So the reason why we are seeing ice loss is because this warm water is melting the ice shelf, and ice shelf is getting thinner. And thinner ice shelf means less buttressing. So the ice is actually in the trough, right? So if you have the thinner ice shelf, that leads to the warm water thinning the ice shelf. That will speed up the ice flow due to the lack of buttressing or reduced buttressing, leading to speed up the ice flow, grounded ice loss, and sea level rise. So that's why oceanographers care about why this warm circumpolar deep water, this warm water is flowing towards the ice. Okay? So the question is how does warm water travel towards the ice shelf cavities, and what controls it? So let's review a little bit of review of what we understood in the past 10 years or so about the processes, ice-ocean interactive processes over the Antarctic continental shelves. So we look at this region. This is Amundsen Sea. This is the region where we see highest melting regions from the Grace Antarctic ice loss. So we zoom in to this location right here, and it looks like this. So for oceanographers, bathymetry is very important, especially if you think about coastal processes, because ocean current mostly follows the isobath, same depth level. So we have to care about how the bathymetry looks like. Here in this region, this is a similar thing. This is just colors. This is in 3D. But when you think about long time ago during Ice Age, right? The ice was very thicker. They eroded. They carved the trough. This is glacially carved trough. It's like a fjord kind of thing. There's a very deep depression right here, and glacially carved trough. There are two connections to the open water. One is here. This is called eastern trough. This is the central trough. But there's a deep depression connected to the open water. So when you think about this, the warm circumpolar deep water is actually following these troughs and flowing all the way towards the ice shelf cavity. That's how it works here. So let's take a look how it looks like in the numerical simulations. I'm going to flip this picture, but in this case, this is the Pine ice shelf, right? This is the Pine ice shelf. And then we are looking at this. So now we are flipping 180 degrees now, but this is the Amundsen Sea. This is open water. We are looking at 552 meter potential temperature. So it's a mid-depth ocean temperature. At the depth, we are looking at this depth. At this depth where we have this warm water, right? We are looking at the depth where there's warm water, and then trying to see how warm water travels to this location. So as you see here, this is the central trough. This is the eastern trough. This is the region. So there's ACC, and then there's Rothschild right here, but we are focusing on this region here. This is the continental shelf part. The blue part is very shallow bathymetry. Warm water is traveling from this central trough and eastern trough, and then joining the margins together, and then following this deepest trough, Pine Island trough, and then flowing all the way towards the ice shelf cavity. So that's basically how the warm water is traveling towards the ice. Okay. If you zoom in to this location, we can look at this like something like this. Here we are looking, again, this is very close to 500 meters. We are now looking at the density level, 27.75, nearly at 500 meters. We are looking at temperature between 1.1 to 1.4. So we are actually seeing tiny little range in temperature, but we are seeing cores of warm water hugging the coast, flowing towards the ice shelf cavities. And this is the ice shelf. This transparent thing is the ice shelf. So we are seeing that, okay, the warm water is traveling towards the ice into the ice shelf cavities, and then this warm water is melting the ice. So this is how, you can probably visualize how now you can think about how, how warm water is traveling towards the ice and contributes to melting. But what did we understood in the past? We have data in this Amundsen Sea, we have data only from 1994. But because of the fact that we realized that the ice shelf is melting very rapidly, we have a lot of data in the past 10, 20, 15 years or so. So what did we learn from it? So the important understanding that, I think we all kind of reached the consensus in the community is that thermocline depth controls ice shelf melt rates. So this, there's a thermocline depth that separates this cold water and warm water, and this depth goes up and down. At the same time, if you see here, there's a bathymetric high here. This is like a subglacial moraine. Therefore, you always find these kind of typical features in under the different ice shelves. And warmest water at the depth has no access to this location because of the subglacial moraine. So what happens is that this mid-depth water, this has access to the ice shelf cavity. So biggest internal variability that has been observed. So this is not a trend. This is the internal variability that happened from 2009 to 2014 or so. We are seeing two different time frames. We see deepened thermocline. And because this mid-depth gets colder, right, and this water mass that goes into the cavity is getting colder. So this is the thermocline depth that controls ice shelf melt rate. That's one of the biggest important findings from our study, coastal studying about ice-ocean interaction. There are several ideas what controls this thermocline depth. Somebody is saying it's related to El Niño La Niña things. Some people are saying, okay, it's dense water formation, as you see. If you create sea ice, maybe you can deepen these layers. But I'm not going to go so much about this today. So that's how warm water is traveling towards the ice. However, it's quite difficult to understand how, what is happening, what's going on in these regions. So in our group, we try to combine both observation and modeling to tackle these questions like what's happening in the Southern Ocean. And then I'll talk a little bit about, observation and modeling things that we are working on today. So what we are doing is actually we are developing different regions of the regional simulations. We develop ECCO downscale regional simulations. And we do this because we really care about model data agreement, because we want to explain what's being observed and what is the driver for the observed changes. So the reason why we have to use, for example, develop regional simulation is because, you've seen this picture already. Warm circumpolar deep water is traveling towards the ice shelf cavities. This is one of the ocean states estimates called ECCO, and it's the exact same section. And they're quite different. Of course, it takes a lot of time for the model development. State estimate, ocean reanalysis development, it takes so long to develop. At the same time, ocean bathymetric data can be updated within a year because polar regions, once ship goes there, we find new data set. So this is actually having quite different data set, different bathymetry. This is another one, SOSI, but they also have very different bathymetry. And also, as I said, thermocline depth, right? This depth goes up and down, controlling the ice shelf melt rates. But we don't really get that. So that's why we have to, I've been working on developing regional simulations. However, just having a regional simulation is not always good because having tiny little parameter, for example, in the sea ice or something, can lead to quite different behaviors. Like what we see very, very cold water at this location here. However, if you look based on the past observation, all observation in the Amundsen Sea, we always find warm water at the depth, cold water at the shallow depth, and this thermocline depth goes up and down. That was the only variability that has been observed in this location. So in my group, we are really doing a lot of different things to achieve as best as possible agreement with observations and try to understand what has been happening. So that's what we are kind of doing. So I thought in the remaining time of the talk today, I thought it would be nice to probably talk about different ice shelf cavities and how diverse the systems are, because I thought that might be interesting for all of the people participating in this conference today. So what I am doing is we are contrasting two different regions. One is Amundsen Sea. This is the highest melting region in West Antarctic, and Totten. This is the region that we are seeing some increase in ice shelf melting, ice loss, and potentially that might be a potential important region for the future sea level rise contribution from Antarctic ice shelf. So we are going back to this picture again. So Amundsen Sea, right? This is Amundsen Sea. We see warm water traveling towards the ice shelf cavity. This is about 150 kilometers. So this ice shelf itself is 40 to 50 kilometers wide. So as you see here, warm water, which is about 1.5 degrees C or 1 degree C, this warm water is almost free access to the ice shelf cavity, right? There's no temperature change from the open water towards the ice shelf cavity. So it's basically, there's a pretty wide trough. Warm water has free access towards the ice shelf cavity and flows into the ice shelf. That's how it looks like for Amundsen Sea. Yeah, so that's what I want to say. Okay, and then so that's basically here Amundsen Sea. This warm circumpolar deep water, there's almost no change in temperature, and that's because there's a very wide trough, and that supports warm water intrusion towards the ice shelf cavity and contribute to the melting. So as I said, what controls the ice shelf melt rates is this is determined by thermocline depth. This depth goes up and down, and there's almost no change observed in temperature, but two water masses, warm circumpolar deep water and this cold winter water, the property remains almost the same, but thermocline depth goes up and down, and that controls the ice shelf melt rates. However, if you look for the East Antarctic, so to summarize, the Pioneer ice shelf, it's a wide pathway of warm water, very little MCW, warm water modification along the way from the open water towards the ice shelf cavity, and the thermocline depth determines the ice shelf melt rates. So let's look on the other side, right? East Antarctic, Totten ice shelf, and what determines the ice shelf melt rates. So Totten, this region, there's observations done by Australians, and they witnessed that there's a warm water, which is about minus 0.4 degrees C. Oh, now we realize it's a quite different temperature now. It's quite colder. And Totten is actually very thicker. So the ice shelf, or ice sheet itself, is very, very thick in the East Antarctic. That's why there are a lot of focus on trying to understand what are the processes, ocean processes, controlling ocean heat intrusion towards this region. However, there has been a lot of icebergs and sea ice, and it was quite difficult to measure in these locations. So I was in Japan, and I was participating in Japanese observation cruises, and we actually did this airborne measurements, trying to understand what's the heat pathways towards this region into the ice shelf cavities in Totten. So based on the observations, we actually find out that there's a pretty warm water which is actually traveling towards Totten. This is actually the region that has never been observed due to very thick sea ice and icebergs. So in contrary to what we observed in this location, that we actually see minus 0.4 degrees C, we see roughly 1.5 to 1 degree C, pretty warm water, which is we actually find in section A. I'm going to go 6 and C, but we also find pretty warm water at this location. Even just a few tens of kilometers, we actually see pretty warm water. However, as we have seen in the section D, that there's a very cold water. So now I actually changed the color scale from minus to 0 degrees C here. So we actually see much, much colder water at the section D, at the ice shelf front. So what we actually find out based on this, this is actually what we find out only after 2015, because the first measurement was in 2015. And then since then we find out that actually there's in the East Antarctic, we have like a bucket, like a big depression. Warm water has pretty much free access to this location. However, if you go very close to the ice shelf cavities, there's a very strong modification that happens right here between the ice shelf cavities and the ice shelves. So what happens here is that actually we have the ship-based measurements too. So not just the helicopters, but the icebreakers has been there at this location. Oh, sorry. The black line, red line, and blue line, these are all temperatures showing that there's a very little, somewhat moderate modification that happens from here to here. However, there's a sharp modification that happens just within a few tens of kilometers from the ice shelf cavities. So the reason why we see this kind of huge change is because the passage from just in front of the ice shelf to the open water is very, very, very narrow. It's roughly 5 kilometers, very, very narrow deep trough. So the warm water has to travel in this narrow trough and flows into the ice shelf cavities. So if you sum up, the system looks like this. In the case of the East Antarctic, we have very, very cold water, and then there's a tiny little warm water which actually comes in as a very thin layers. And this circumpolar deep water is traveling towards the ice and indicating that when there's a tiny little bit of heaving, this system is very, very sensitive to the change in thermocline depth. So if you summarize total ice shelf, it's like a bucket, like big depression, deep thermocline, and narrow pathways at the ice shelf front. And this is indicating that ice shelf melt is highly sensitive to the heaving of thermocline depth, thermocline depth. Can I talk one more minute? All right. Quickly. So, okay, I think I'll stop here. It's fine.
You've all seen the question quickly, so if anyone wants to ask about that, feel free to do it. Thanks, Yoshi. We have time. Yeah, we have time for questions.
Thanks, Yoshi. That was great. I was wondering, because I'm not so familiar with the Totten area, do you have an understanding of how long the Totten area has been locked in by sea ice and icebergs in this way? And do you think that that could contribute, that the surface forcings associated with that could contribute with the deeper hydrographic state?
Right. So there has been pretty big fast ice. I don't know if you can see that, but here, this part is very big fast ice, and this has been locked. And this part is a granite icebergs, and that's why there's an opening, because there's a granite iceberg, and no sea ice can penetrate from east to west at this location. So Polinia always happened, and there's a very big fast ice, but this has broken off very recently, like 3 or 4 years ago. So the situation has changed quite a lot in the past 3-4 years.
The question was for Yoshi. Otherwise, I was curious, you had the slide with the global, regional, and regional simulation, including observations, and I was wondering if you could comment on the differences between the regional and the one in which you included the data, and especially when you do optimization, what are the main differences, how you had to adjust the model's parameters or forcing to get to this more realistic picture of this region?
So we have been doing a lot of things, but we also try employing green function approach or joint method to optimize. But in my experience, at the end, because of due to quite high non-linearity that happens there, a joint method doesn't really work very well. So we ended up, based on experience and lots of forward simulation, that's something that we realized that achieves the best agreement. But having said that, we really carefully compare a lot of different things like mean state, internal variability, sea ice, ice melting, a lot of different things we compare. And then we also try to understand physical mechanism that is controlling the changes. So for example, in the case of the East Antarctic, we actually simulating, so in the East Antarctic, we see thicker thermocline, right? And then the halocline thermocline is way thicker. So the thing that I actually wanted to talk about for the East Antarctic simulation is that we also simulate East Antarctic, we also develop East Antarctic simulation as well. And then we realized that one of the simulations that we have published, this is Nakayama et al. 2021, so I'm actually saying that my simulation is very, very bad. So this was the observations. Let me say that this is developed before the observation we got the observations. So we did not know that it's so bad. But we realized it's very, very bad. And then we tried we have optimized different parameters so that we now, this is the work from my student Hyogo et al. We now able to get better state, including very cold winter water and deep halocline. And by achieving these, we can, so not just to optimize the model parameter, but we can say, okay, by analyzing these, the difference between the previous model and this model, we can say, oh, what might be the mechanism that is controlling this. So that's something that we also want to do as well in our group.
So what were the parameters that had to be adjusted?
Okay. So in this case, the wind and iceberg melt and surface heat flux was adjusted. That was the three main parameters. And then if you, for example, if you think about the wind, this is because if you have more westward wind on the shelf, that will create a lot more Ekman downwinding. And that is actually, the Ekman downwinding is actually one of the most important reasons, seeing somewhat homogeneous thick winter water with a pretty homogeneous salinity as well.
Thank you. Thanks.
Yep, thank you very much.
Sorry, I didn't see it. Sorry. Oh, yeah. Do you want to use the mic, please, so people can. Thanks a lot.
Couple questions, if I may. So you showed Amundsen Sea and Totten. Where else would you go? What is another interesting place, or other interesting places in your view that you would go and collect?
Oh, where's the interesting place? I think everywhere is pretty interesting. So we are, in our group, we are looking at all of these regions around here. I mean, Antarctica, bottom water formation is very important. And what's the implication for material exchange and carbon cycle? I think it's a very important topic. At the same time, even if you think about just ice shelf ocean interaction, it's very, very different in different regions, as you say. As you have seen, Amundsen Sea, shallow thermocline, free pathway, warm water. East Antarctic, very thick thermocline, maybe very sensitive to slight heaving. Weddell is very different, right? I mean, as you know, Antarctic bottom formation, how they interact with slope, and then there's also interaction with slope current as well. So I think wherever you look, it's very interesting.
And another question, if I may. Most observations are from like summertime, right? So wouldn't you be summer biased in your models, simulations, and everything? Or how do you deal with that if you optimize parameters?
Very good point. We also look at limited available moorings. At the same time, there are many, I mean, it's difficult to get the summer state correct. So getting the summer state correct, I think, is a good improvement. Having said that, at the same time, we also look at the mooring time series and try to get seasonal and internal variability based on the limited data available. Thank you.
Thank you.